Hello, we spoke previously before about philosophies of design, and now I wanted to look at some of the brass tacks of things, specifically the mechanics of materials. So we'll look at solid behavior. We'll consider fluids, both gases and liquids later, and thermodynamics and heat transfer. All of those are important elements for the designer to understand these things in a visceral sense so that when you're designing, they come right to the forefront. You have a good tacit understanding of the behavior of materials. And we're going to focus on solids right now. And when we look at this sounds sort of like engineering. It sounds as if it's science. And of course, we tap into a lot of things in design. We tap into whatever we need to tap into. So whether it's elements of design such as symmetry, repetition, rhythm, balance, proportion, harmony, movement, color, texture, or the compositional elements of design in terms of that we see in artwork and photography that are important, we'll tap into whatever we need to. These are sort of approaches that resonate deeply, some in sort of this positivistic notion that we've talked about before, but even in qualitative research, there are certain things that we can tap into, certain sciences that we can tap into to an end. So in this case, we're looking at how materials behave, and that's a reasonable question for a designer to wonder about. And when you look at how something behaves, you first have to understand the loads that are applied to it. So again, we're talking about solid materials, we're talking about anything from bookshelves to laptops to cars to whatever, things that are made out of solids. And here we say these things are subject to the loads. There are people stand on them, they kick them, they throw them, snow weight is landed upon them, ice expands and pushes on them, birds land on them, and all kinds of physical duress are encountered by things that we design. So we want to understand how they behave. And what you typically have are two types of loads. You have a load in tension, something that's pulling things apart, or a load in compression, things that are pushing things together. Those are the two principal loads. So normally you would draw a free body diagram showing how your part is subjected to a variety of loads, just so you get a sense for it. And that's a whole other thing that really doesn't lend itself as well to video lecture, in the sense that you want to anticipate unanticipated loads, but you certainly want to cover all loads that something could handle, whether it be in shipping or during the whole shopping experience or installation or usage and whatnot. It's not just how something's used, there's a whole sequence of events that occur that cause the product, the design to be subject to all sorts of things. And low temperatures, high temperatures, salt spray, vibration, all sorts of things. But here we're looking at loads, and these loads are turned into stress. In other words, a load divided by an area is a stress. And materials can only handle a certain amount of stress. And these numbers are all out there. You can find out what these numbers are. But again, the typical loads are tension and compression. That's normally what you look at. But I think it's more convenient to consider 5 types of loads. And even though in theory these can all be reduced to tension and compression, it's just a good practical way to keep your hands around this stuff, is to think of 5 loads. And that would be tension, compression, torsion, which is a twisting, shear, which is a sliding, and flexure, which is a combination of compression and tension. So again, that would be tension, compression, shear, we'll put it in that order, torsion, and flexure. So if we look at those 5 loads, tension again is pulling molecules apart, compression is pushing molecules together, shear is sliding molecules across each other, and that becomes really important in fluid dynamics, because a solid is a fluid with an infinite viscosity, almost an infinite resistance to flow. So the only difference between water and steel is that water has a viscosity that's less than infinity. That's kind of a convenient way to look at it. It's not completely true, but that's a good way to think of it. So solids it's all sort of a continuum. And then you have a torsion, which is, again, the twisting resistance of something. And that's something that often people don't think about. You can even get torsional vibrations in shafts. So you can have gears that are having problems and you don't know why. It's because you have this sort of oscillatory vibration going on in a shaft, caused by it vibrating at some resonant frequency. And so that's kind of more sophisticated engineering concerns, but it's something to mull over anyway. Also, you can have something that's very strong. It seems to be strong, but it twists very easily. So a structure has to be strong in flexure and torsion typically, otherwise you have problems depending on what's going on. And for example, bones, the human bones are tubes, and tubes with a hard material on the outside and a spongy material on the inside. And tubes are really good for handling torsion because the moment of inertia is very high in all axes, and it's a very good way to handle loads like that. Where you know where the load is going to come from exactly, that's where you see I-beams. And I-beams are like in girders and bridges or buildings and such. And they're very strong for the amount of material put in them on a certain plane. And so that's important too, to understand how loads are applied. So if you're designing a bridge and you know most of the loads are going to be in a certain direction, you can make beams that work really well that way. But if you can't predict the direction of loads, then you're in trouble if you design something that's strong only in one way. And flexure is the last of these 5 loads, and that's this combination of tension and compression, and that's it's an interesting phenomenon. Most things are subject to flexure. So a cantilever beam, like a diving board, when you stand on it, you're putting the top fibers of the diving board in tension, the bottom fibers in compression. And the amount of tension is proportional to a couple things. And I say tension because that's usually how things break. They fail in tension. And it's proportional to the moment arm. So the further you walk out on the diving board, the higher is the tension at the point where the diving board joins some solid wall. And it's also proportional to the distance from the center of the diving board, the center line of it, to the outer fiber or the top of the diving board. So it would be half the thickness of the diving board. So the middle of the diving board, if you look at it from an end view, you could drill holes right through the middle of the diving board and there's really no stress there. But if you drill at the top of the diving board or saw at the top of the diving board, you seriously weaken it. So that's where flexure comes into play. Then there's some what I call weird loads, loads that aren't so common, but they're really important. In fact, they're so important that I give them a special category of weird loads because they're frequently what cause things to fail. And these are stress concentrations, fatigue, impact, corrosion, and buckling. Buckling would be the last one. And if we look at these, impact, you're familiar with it from a hammer. You hammer something and you transmit a great deal of force into something. You multiply the force. And what happens is you create stress waves. And stress is like sound. It's a movement. It's a compression and rarefication of molecules through a solid. And these can stack up and increase stresses in a material. So you can amplify loads by impact. I'll jump to buckling. Buckling, you're familiar with things that are long and skinny tend to buckle, and they buckle at loads much lower than the theoretical strength of the material. So, in other words, a column won't fail through compressive failure, it will fail in buckling, which is kind of the form of flexure. Then you have stress concentrations. That's a big issue. Stress concentrations are amplifications of stress caused by changes in geometry. So sharp corners, nicks, these kind of things can cause or do cause stress concentrations. And it's normally where failure initiates. So, for example, if you have a shaft with a corroded surface, the shaft is actually stronger if you grind down the surface so it's smooth, even though you've reduced the diameter, than if you leave all these little corrosion points that act as stress concentrations. Keyways and shafts are problems, sharp corners are problems, all these kind of things. Then you have corrosion, and corrosion destroys material, so it reduces the area, and that's a whole separate investigation. Corrosion is caused by donating electrons, when one material donating excuse me, electrons to another material, and that shedding of electrons degrades the material. And in the case of steel, the product, rust, is larger volumetrically and it flakes off, and some things like aluminum and titanium and chromium steel, the oxide layer bonds tightly to the material and it gives it some protection. Then fatigue is typically the probably the leading cause of mechanical failure. Excuse me. And fatigue is the weakening of the material due to repeated stress cycles. So something like if you're jumping on the diving board a million times, the diving board will get weaker. The material strength will get weaker than what's advertised. So the fatigue strength is typically, or if you want infinite cycles, stress cycles, typically the maximum strength can only be about half of the yield strength of the material to allow it to last an infinite length of time. Fatigue is really important. It's often determined experimentally, and it's a real critical parameter because it's different than the yield strength that's available in guides. So what often corrosion works with fatigue, so corrosion will work on a metal and weaken it and cause stress concentrations. You'll reduce the area, and fatigue will work in conjunction with that to cause something to break. So you can have something that's worked very well for a long time and then suddenly it breaks, and that's often due to fatigue failure. So that's sort of the summary of the standard loads: tension, compression, shear, torsion, and flexure, and these sort of weird loads, stress concentrations, fatigue, impact, buckling, and corrosion. It's good to put your fingers around those to get a sense for how those behave. Thank you.